The story of how humanity came to understand what a supernova actually is cannot be separated from the broader history of how people have observed the sky, interpreted celestial events, built instruments, developed physical theories, and gradually assembled a picture of the universe that bears almost no resemblance to what any prior generation imagined. To understand what really happens when a star goes supernova, it is necessary to begin not with the explosion itself, but with the centuries of accumulated observation, misinterpretation, tentative correction, and eventual theoretical breakthrough that made it possible to ask the question in a meaningful way at all. The phenomenon is not simply an astronomical event. It is a process that connects nuclear physics, thermodynamics, general relativity, neutrino physics, the chemistry of the interstellar medium, the formation of subsequent generations of stars, and ultimately the existence of the heavy elements that constitute planets and living organisms. Each of these connections was discovered independently, often by researchers who had no idea their work would eventually feed into a unified account of stellar death, and the synthesis that exists today is still incomplete, still contested in important details, and still being revised by observations that arrive from increasingly sophisticated instruments. The earliest recorded observations of what we now call supernovae were made by Chinese astronomers, and to a lesser extent by Korean, Japanese, Arab, and possibly European observers, though the European records are sparser and harder to interpret. The Chinese astronomical tradition, maintained by imperial bureaucracies over many centuries, produced systematic records of what were called guest stars, meaning stars that appeared where none had been seen before, and then faded over weeks or months. The most famous of these is the guest star of 1054, recorded in Chinese and Japanese sources, which appeared in the constellation we now call Taurus, and remained visible to the naked eye for nearly 2 years. The remnant of that explosion is the Crab Nebula, one of the most studied objects in modern astrophysics. What is important about these early records is not merely that they document the events, but that they reveal something about the intellectual frameworks within which those events were interpreted. In Chinese cosmology, guest stars were understood as omens, signs bearing political or moral significance, and the astronomical bureaus that recorded them did so in part because the appearance of such phenomena was believed to reflect on the mandate of the ruling dynasty. This meant that the observations were preserved with considerable care, because they had political consequences, but it also meant that the physical nature of the events was not the primary concern of the observers. The question of what a guest star actually was, in terms of its distance, luminosity, or physical mechanism, simply did not arise within that framework. In the European tradition, the situation was complicated by the Aristotelian cosmology that dominated natural philosophy from antiquity through the late medieval period. Aristotle's physics drew a sharp distinction between the sublunary world, where change and corruption occurred, and the superlunary realm, where celestial bodies moved in perfect, unchanging circles. Within this framework, a new star appearing in the sky was deeply problematic, because it implied change in a region of the cosmos that was supposed to be immutable. When Tycho Brahe observed a bright new star in 1572, in the constellation Cassiopeia, he undertook careful measurements of its parallax and concluded that it was far beyond the Moon, in the realm of the fixed stars. This was a direct challenge to Aristotelian cosmology, and Tycho's publication of his findings contributed significantly to the gradual erosion of the old physics. Johannes Kepler observed another such event in 1604, and again careful measurement showed that the object was at stellar distances. These two events, now known as Tycho's supernova and Kepler's supernova, are the last supernova to have been observed in our own galaxy with the naked eye. The fact that no galactic supernova has been observed since 1604 is itself a statistically interesting point, given that estimates of the galactic supernova rate suggest roughly 1 to 3 per century. The most likely explanation is that subsequent events have been obscured by interstellar dust, which absorbs visible light and can render even an extremely luminous event invisible to observers on Earth. The remnants of several such events have been identified through radio and X-ray observations, confirming that supernovae have occurred in the Milky Way since 1604 but were simply not seen. The transition from observing supernovae as unexplained celestial phenomena to understanding them as physical processes required several independent developments in physics that unfolded over the 19th and early 20th centuries. The first was the development of spectroscopy, which allowed astronomers to determine the chemical composition and physical conditions of distant objects by analyzing the light they emitted or absorbed. The second was the development of nuclear physics, which eventually provided the energy source that powers stars and makes their explosive deaths possible. The third was the development of general relativity, which describes the behavior of matter under extreme gravitational conditions and predicts the existence of objects like neutron stars and black holes, which are the remnants left behind by supernovae. None of these developments occurred in isolation, and each drew on work in other areas of physics, mathematics, and observational astronomy in ways that were not always obvious to the researchers involved. The understanding that stars are powered by nuclear reactions was not achieved until the late 1930s, when Hans Bethe and others worked out the details of nuclear fusion in stellar interiors. Before that, the energy source of the Sun and other stars was one of the great unsolved problems of physics. Lord Kelvin and Hermann von Helmholtz had proposed in the 19th century that gravitational contraction could power the Sun, but calculations showed that this mechanism could sustain the Sun's luminosity for only about 20 million years, which was already in conflict with geological and biological evidence suggesting that the Earth was much older. The discovery of radioactivity by Henri Becquerel in 1896 and the subsequent realization that atomic nuclei contained enormous amounts of energy opened the possibility that nuclear processes might be responsible, but the specific reactions involved were not identified for several more decades. Arthur Eddington, in the 1920s, proposed that the fusion of hydrogen into helium could power the Sun, but the detailed reaction chains were not worked out until Bethe's work in 1938 and 1939. This is relevant to the supernova problem because the entire sequence of events leading to a supernova is determined by the nuclear reactions that occur in a star's interior, and understanding those reactions is prerequisite to understanding why some stars explode and others do not. A star spends most of its life in a state of approximate equilibrium, in which the inward pull of gravity is balanced by the outward pressure generated by nuclear fusion in the core. The fusion of hydrogen into helium releases energy because the helium nucleus has slightly less mass than the 4 hydrogen nuclei that combine to form it, and the mass difference is converted to energy according to Einstein's famous relationship between mass and energy. This energy heats the stellar interior and creates thermal pressure and radiation pressure that support the star against gravitational collapse. The rate at which a star burns its nuclear fuel depends on its mass. More massive stars have higher core temperatures and pressures, which drive nuclear reactions at a much faster rate. This means that counterintuitively, more massive stars have shorter lifetimes than less massive ones, despite having more fuel available. The Sun, with a mass of about 1 solar mass, will spend roughly 10 billion years on the main sequence, fusing hydrogen in its core. A star with 10 solar masses will exhaust its hydrogen in about 20 million years. A star with 25 solar masses might last only 7 million years. These timescales are important because they determine the rate at which supernovae occur in a given galaxy, and they also determine the chemical enrichment of the interstellar medium. Since the heavy elements produced in massive stars are returned to the gas from which new stars form only when those stars die. When a star exhausts the hydrogen in its core, what happens next depends critically on its mass. For stars below about 8 solar masses, the core contracts and heats up, and hydrogen fusion continues in a shell around the now helium core. The core eventually becomes hot enough to fuse helium into carbon and oxygen, but these stars never reach the temperatures required to fuse heavier elements. They end their lives by shedding their outer layers as planetary nebulae and leaving behind a white dwarf, a dense remnant supported by electron degeneracy pressure. White dwarfs are relevant to the supernova story in a different way, which will be discussed later. But the point for now is that low and intermediate mass stars do not undergo core collapse supernovae. For stars above roughly 8 solar masses, the situation is fundamentally different. After exhausting hydrogen in the core, the star begins a sequence of fusion stages, each one burning the ash of the previous stage as fuel. Helium fuses to carbon and oxygen. Carbon fuses to neon, sodium, and magnesium. Neon fuses to oxygen and magnesium. Oxygen fuses to silicon, sulfur, and other elements in that mass range. And finally, silicon fuses to iron group elements, primarily iron 56 and nickel 56. Each successive stage occurs at a higher temperature and pressure than the last, and each lasts for a shorter time. Hydrogen burning in a massive star's core might last millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning lasts perhaps 1,000 years. Neon burning lasts about a year. Oxygen burning lasts months. Silicon burning, the final stage, lasts only about a day. The reason for this dramatic acceleration is that each successive reaction releases less energy per unit of fuel consumed, while the star's luminosity, which is set largely by its mass and structure, remains high or even increases. The star must burn fuel faster and faster to maintain the pressure that supports it against gravity. The structure of a massive star at the end of its life is sometimes described as resembling an onion, with concentric shells of different composition. The outermost layers are still hydrogen. Below that is a shell of helium, then carbon and oxygen, then neon and magnesium, then oxygen and silicon, and finally, at the center, a core of iron group elements. This layered structure is a direct consequence of the sequential fusion stages, and it is physically real, though the boundaries between layers are not perfectly sharp and there is some mixing between zones. The iron core is the endpoint of this sequence, and the reason it is the endpoint is one of the most important facts in nuclear physics. Iron 56 has the highest binding energy per nucleon of any nucleus, meaning that no energy can be released by fusing iron into heavier elements or by splitting it into lighter ones. The fusion of lighter elements into iron releases energy, and the fission of heavier elements into lighter ones also releases energy, but iron itself sits at the bottom of the energy curve. When a star builds up an iron core, it has reached a dead end. There is no further nuclear reaction that can provide the energy needed to support the star against gravity. The iron core grows as silicon burning continues in the shell surrounding it, and the core is supported not by thermal pressure from nuclear reactions, but by electron degeneracy pressure, the quantum mechanical resistance of electrons to being squeezed too closely together. This is the same force that supports white dwarfs, but there is a critical difference. A white dwarf is a relatively cool, stable object that will persist essentially forever, slowly radiating away its residual heat. An iron core, by contrast, is being heated and compressed by the ongoing nuclear burning in the surrounding shells and by the weight of the overlying layers of the star. The core grows until it approaches a critical mass known as the Chandrasekhar limit, approximately 1.4 solar masses, beyond which electron degeneracy pressure can no longer support it. The precise value of this limit depends on the composition and entropy of the core, and in practice, the effective Chandrasekhar mass for an iron core can be somewhat different from the canonical value. But the basic physics is the same. There is a maximum mass that electron degeneracy pressure can support, and when the core exceeds that mass, it collapses. The collapse, once it begins, is extraordinarily rapid. The core has a radius of roughly the size of the Earth, about 6,000 kilometers, and it collapses to a radius of about 10 to 15 kilometers, the size of a city, in less than 1 second. The infall velocities reach a significant fraction of the speed of light, on the order of 70,000 kilometers per second. The temperatures rise to hundreds of billions of degrees, and the densities exceed those of atomic nuclei. To put this in perspective, a teaspoon of the material at the center of the collapsing core would have a mass of several billion tons. These conditions are so extreme that they push matter into a regime of physics that cannot be replicated in any terrestrial laboratory, and our understanding of what happens depends on a combination of theoretical calculations, computer simulations, and indirect observational evidence. Two critical processes occur during the collapse that determine its outcome. The first is the photodisintegration of iron nuclei. At the extreme temperatures in the collapsing core, high-energy photons break apart iron nuclei into helium nuclei and free neutrons. This reaction absorbs energy, about 124 million electron volts per iron nucleus, which is energy that was released during the earlier fusion stages. In effect, the core is undoing in an instant the nuclear processing that took the star millions of years to accomplish. The energy absorbed by photodisintegration reduces the thermal pressure in the core, accelerating the collapse. The second process is electron capture, also called neutronization or inverse beta decay. At the extreme densities in the core, electrons are forced into protons, converting them to neutrons and releasing electron neutrinos. This process removes electrons from the core, reducing the electron degeneracy pressure that was providing the last remaining support against gravity. It also produces an enormous flux of neutrinos, which initially escape freely from the core because the matter, despite its extreme density, is still transparent to neutrinos under normal conditions. These two processes, photodisintegration and electron capture, together drain the core of the pressure it needs to resist gravity, and the collapse becomes essentially freefall. The inner part of the core, roughly 0.6 to 0.8 solar masses, collapses homologously, meaning that all parts of it fall inward at the same fraction of the local freefall speed, maintaining a roughly uniform structure. The outer part of the core collapses supersonically, raining down on the inner core at velocities that exceed the local sound speed. When the inner core reaches nuclear density, about 2.3 times 10 to the 14th grams per cubic centimeter, the strong nuclear force becomes repulsive at very short distances and suddenly resists further compression. The inner core stiffens abruptly, and the infalling material bounces off this newly rigid core, generating a powerful shock wave that propagates outward through the still infalling outer core. This is the core bounce, and it was initially hoped that the shock wave generated by the bounce would have enough energy to propagate outward through the entire star and eject the outer layers, producing the supernova explosion. This is called the prompt shock mechanism. However, computer simulations performed from the 1960s onward consistently showed that the shock stalls. As the shock moves outward through the iron core, it encounters material still falling inward at high velocity, and it also passes through a region where the infalling iron is being photodisintegrated, absorbing energy from the shock. The combination of the ram pressure of the infalling material and the energy losses from photodisintegration drains the shock of its kinetic energy, and within about 10 to 20 milliseconds of the bounce, the shock comes to a halt, typically at a radius of about 100 to 200 kilometers. It becomes a standing accretion shock, with material continuing to fall through it onto the proto-neutron star forming at the center. The failure of the prompt shock mechanism was a major problem for supernova theory. Supernovae are observed to occur, and the kinetic energy of the ejected material can be measured from the expansion velocities and masses involved, giving total explosion energies on the order of 10 to the 51 ergs, a unit known in the field as 1 Beth, or 1 Fo, for 10 to the 51 ergs. The gravitational binding energy released by the collapse of the core is about 100 times larger than this, roughly 3 times 10 to the 53 ergs. So in principle, there is more than enough energy to power the explosion. But almost all of this energy, about 99%, is carried away by neutrinos, which stream out of the proto-neutron star as it cools and deleptonizes over a period of about 10 seconds. Only about 1% of the gravitational energy goes into the kinetic energy of the explosion, and only about 0.01% into the light that makes the supernova visible. The challenge for theorists has been to explain how the stalled shock is revived, how some of the enormous energy carried by neutrinos or stored in other forms is transferred to the shock to restart the explosion. The leading candidate mechanism for shock revival is the delayed neutrino heating mechanism, proposed by James Wilson and refined by Hans Thomas Janker, Adam Burrows, and many others. The basic idea is that a small fraction of the neutrinos streaming out of the proto-neutron star are absorbed by the material just behind the stalled shock, in a region called the gain layer. The neutrinos deposit energy in this layer, heating it, and the resulting increase in thermal pressure eventually revives the shock and drives it outward. The process is delicate because the efficiency of neutrino heating depends on the neutrino luminosity, the neutrino energy spectra, the radius of the gain layer, and the density and composition of the material in that layer, all of which are changing rapidly as the collapse proceeds. In spherically symmetric, one-dimensional simulations, the neutrino heating mechanism generally fails to produce explosions, or produces explosions that are too weak compared to observations. This was a persistent difficulty that led some researchers to question whether the mechanism was correct at all. The breakthrough came with the development of multidimensional simulations in 2 and then 3 dimensions, which showed that hydrodynamic instabilities play a critical role in the explosion mechanism. 2 instabilities are particularly important. The first is convection, which develops in the gain layer because the neutrino heating creates a region that is convectively unstable, with hotter material rising and cooler material sinking. The convective motions bring material closer to the proto-neutron star, where it absorbs more neutrino energy, and then carry that energy upward to the stalled shock. This increases the effective dwell time of material in the gain layer, allowing it to absorb more energy than it would in a stationary, spherically symmetric flow. The second instability is the standing accretion shock instability, known by the acronym SASI, which is a large-scale oscillation of the shock front that develops spontaneously from small perturbations. The SASI causes the shock to slosh back and forth, sometimes in a dipolar mode, with one hemisphere expanding while the other contracts, and this asymmetry helps to funnel energy into particular directions, breaking the symmetry of the problem and facilitating the explosion. The interplay between neutrino heating, convection, and the SASI is complex and not fully understood. 3-dimensional simulations, which have become feasible only in the last 15 years due to advances in computing power, show behavior that differs in important ways from 2-dimensional simulations, and the results are sensitive to the input physics, including the nuclear equation of state, the neutrino interaction cross-sections, and the initial conditions provided by stellar evolution models. Despite these uncertainties, a broad consensus has emerged in the computational astrophysics community that the delayed neutrino heating mechanism, augmented by multidimensional fluid instabilities, is the primary mechanism driving core collapse supernovae for most progenitor masses. There are, however, alternative or supplementary mechanisms that may operate in some cases, including magneto-rotational effects in rapidly rotating progenitors, which can produce jet-driven explosions, and the acoustic mechanism proposed by Adam Burrows, in which sound waves generated by oscillations of the proto-neutron star transfer energy to the shock. The relative importance of these mechanisms for different progenitor stars remains an active area of research. The proto-neutron star left behind after the explosion is an extraordinarily dense and hot object, initially with a temperature of several tens of billions of degrees and a radius of about 50 to 60 kilometers. Over the next 10 to 30 seconds, it cools by emitting neutrinos, contracts to its final radius of about 10 to 15 kilometers, and becomes a neutron star. The neutrino emission during this cooling phase carries away the bulk of the gravitational binding energy released in the collapse, approximately 3 times 10 to the 53 ergs, and this neutrino signal was directly detected for the first time from supernova 1987A, which occurred in the Large Magellanic Cloud on February 23, 1987. The Kamiokande 2 detector in Japan detected 12 neutrinos. The Irvine, Michigan Brookhaven detector in the United States detected 8, and the Baksan detector in the Soviet Union detected 5, all within a window of about 13 seconds. These 25 neutrinos, detected from a supernova roughly 168,000 light-years away, confirmed the basic theoretical picture of core collapse and neutrino cooling, and they constituted one of the foundational observations of neutrino astronomy. The detection was possible because of the enormous number of neutrinos produced. Roughly 10 to the 58 neutrinos are emitted during the cooling of the proto-neutron star, and even at the distance of the Large Magellanic Cloud, the neutrino flux at Earth was about 10 billion per square centimeter per second for those few seconds. The neutron star that remains after the supernova is itself a remarkable object. Its density is approximately 2 to 3 times the density of an atomic nucleus, about 5 times 10 to the 14 grams per cubic centimeter, and its gravitational field is so strong that the escape velocity from its surface is about 1/3 the speed of light. The internal structure of a neutron star is still not fully understood, because it depends on the equation of state of matter at supranuclear densities, which is not well constrained by laboratory experiments. The outer crust is thought to consist of a lattice of neutron-rich nuclei immersed in a gas of free electrons. Below this, the inner crust contains nuclei that become increasingly neutron-rich with depth, until at some point, neutrons begin to drip out of the nuclei and form a superfluid component. The outer core is believed to be a fluid of neutrons, with a small admixture of protons, electrons, and muons, and the neutrons and protons may form superfluid and superconducting states, respectively. The inner core, at the very center of the neutron star, is the least understood region. It may contain exotic forms of matter such as hyperons, kaon or pion condensates, or even deconfined quark matter, where the quarks that are normally bound inside protons and neutrons become free to move independently. The question of whether quark matter exists in neutron star cores is one of the major open problems in nuclear astrophysics, and it has implications for the maximum mass that a neutron star can attain before collapsing to a black hole. If the collapsing core is too massive to be supported as a neutron star, which occurs when the remnant mass exceeds approximately 2 to 2.5 solar masses, the exact value depends on the unknown equation of state, then no known force can halt the collapse and the core forms a black hole. This can happen either promptly if the core is sufficiently massive, or with a delay if a neutron star initially forms but then accrues additional mass from fallback of material that was not successfully ejected. The formation of a black hole instead of a neutron star has observable consequences. It may lead to a weaker or failed explosion, since the neutrino-driven mechanism depends on the presence of a hard surface, the proto-neutron star, to generate the neutrino luminosity that drives the shock. There is observational evidence that some massive stars do disappear without producing a bright supernova, consistent with the formation of a black hole by direct collapse, though the evidence is still limited and somewhat indirect. Surveys that monitor large numbers of stars for disappearances, such as the work of Christopher Kochenek and collaborators, have identified a small number of candidate failed supernovae, but confirming these identifications is challenging. Returning to the explosion itself, the shock wave generated by the revived mechanism propagates outward through the star's envelope at velocities of tens of thousands of kilometers per second. The time it takes for the shock to reach the surface depends on the size of the star. For a blue supergiant, which has a relatively compact envelope with a radius of perhaps 30 to 50 solar radii, the shock breakout occurs several hours after core collapse. For a red supergiant with a radius of several hundred to 1,000 solar radii, the shock may take a day or more to reach the surface. When the shock breaks through the stellar surface, it produces a brief, intense burst of ultraviolet and X-ray radiation called the shock breakout, which lasts from seconds to minutes depending on the progenitor's structure. This shock breakout signal has been observed in a handful of supernovae, most notably by the Kepler Space Telescope in 2016, which caught the initial flash from a Type II Ca-P supernova in a distant galaxy. The detection of the shock breakout provides direct information about the radius of the progenitor star and the energy of the shock, and it represents one of the earliest observable signals from a supernova after the neutrino burst. After shock breakout, the supernova becomes visible as an expanding, cooling fireball. The luminosity and spectral evolution of the supernova over the following days, weeks, and months depend on several factors: the mass and composition of the ejected material, the energy deposited by the shock, the radius of the progenitor, and the amount of radioactive nickel-56 synthesized during the explosion. Nickel-56 is produced by explosive nuclear burning as the shock passes through the silicon and oxygen layers of the star, and it plays a central role in powering the light curve of the supernova after the initial phase. Nickel-56 is radioactive, with a half-life of about 6.1 days, and it decays to cobalt-56, which is itself radioactive with a half-life of about 77.3 days. Cobalt-56 decays to stable iron-56. The gamma rays and positrons emitted in these decays are absorbed by the expanding ejector and converted to thermal radiation, which maintains the supernova's luminosity over weeks to months. The amount of nickel-56 produced varies from one supernova to another, typically ranging from about 0.01 to 0.1 solar masses, but in some cases reaching as much as several tenths of a solar mass or more. The observational classification of supernovae is based on their spectra and light curves, and it is worth noting that this classification scheme was developed empirically, before the physical mechanisms were understood, and it does not map in a straightforward way onto the physical categories of explosion mechanism. The two main classes are Type 1 supernovae, which lack hydrogen in their spectra, and Type 2 supernovae, which show hydrogen. Type 1 is further divided into Type Ia, which show a strong silicon absorption feature, and Type Ib and Ic, which lack silicon but show or lack helium respectively. Type 2 is divided into several subclasses based on light curve shape and spectral properties. The physical interpretation is that Type 2 supernovae are core collapse events in stars that have retained their hydrogen envelopes, while Type Ib and Ic supernovae are core collapse events in stars that have lost their hydrogen envelopes, and, in the case of Ic, their helium envelopes as well, through stellar winds or binary interaction before the explosion. Type Ia supernovae, on the other hand, are believed to have an entirely different physical origin. They are thermonuclear explosions of white dwarfs, not core collapses of massive stars. The Type Ia mechanism deserves detailed discussion because it represents a fundamentally different type of supernova, one that involves not the gravitational collapse of a core, but the complete thermonuclear detonation of an entire star, with no compact remnant left behind. A white dwarf is the remnant of a low or intermediate mass star, typically composed of carbon and oxygen, with a mass below the Chandrasekhar limit. If a white dwarf is in a binary system with a companion star, it can accrete material from the companion, either through Roche lobe overflow, in which the companion star fills its gravitational potential lobe and matter flows onto the white dwarf, or through a merger of two white dwarfs that in spiral due to gravitational wave emission. As the white dwarf's mass approaches the Chandrasekhar limit, the temperature and density in its interior rise to the point where carbon fusion ignites. Unlike the stable, regulated fusion in a main sequence star, the fusion in a white dwarf is explosive, because the degenerate equation of state means that the pressure does not increase with temperature in the way needed to regulate the burning. The temperature increases, which increases the fusion rate, which increases the temperature further in a thermonuclear runaway. A detonation wave propagates through the white dwarf, fusing most of the carbon and oxygen into intermediate mass elements, silicon, sulfur, calcium, and iron group elements, nickel-56 iron, and the entire star is disrupted, with no remnant left behind. The single degenerate and double degenerate scenarios for Type Ia progenitors have been debated for decades, and neither has been definitively established as the dominant channel. In the single degenerate scenario, the white dwarf accretes from a non-degenerate companion, such as a main sequence star, a subgiant, or a red giant. In the double degenerate scenario, two white dwarfs spiral together due to gravitational wave emission and merge. There are theoretical difficulties with both scenarios. The single degenerate scenario faces the problem that steady hydrogen accretion onto a white dwarf tends to produce nova outbursts that may eject as much material as is accreted, making it difficult for the white dwarf to grow in mass. The double degenerate scenario faces the problem that the merger of two white dwarfs may, in some cases, lead to an accretion-induced collapse to a neutron star rather than a thermonuclear explosion, depending on the mass ratio and the details of the merger process. There are also sub-Chandrasekhar mass models, in which a white dwarf with a mass well below the Chandrasekhar limit detonates when a layer of accreted helium on its surface ignites and drives a detonation wave into the carbon-oxygen core. These models can potentially explain some of the diversity observed among Type Ia supernovae. The progenitor problem for Type Ia supernovae remains one of the major unsolved problems in stellar astrophysics, and it has implications beyond the field, because Type Ia supernovae are used as standardizable candles for measuring cosmological distances. It was the observed relationship between the peak luminosity and the rate of decline of Type Ia light curves, discovered by Mark Phillips in 1993 and calibrated by many subsequent studies, that enabled the supernova cosmology projects led by Saul Perlmutter, Brian Schmidt, and Adam Rees to discover the accelerating expansion of the universe in 1998, a discovery that was awarded the Nobel Prize in Physics in 2011. The nucleosynthesis that occurs during a supernova whether core collapse or thermonuclear, is responsible for producing a significant fraction of the elements in the periodic table. The precise yields depend on the type of supernova, the mass and metallicity of the progenitor, and the details of the explosion. Core collapse supernova are the primary source of elements from oxygen through calcium, and they also contribute to the production of iron group elements. Though type Ia supernovae are believed to be the dominant source of iron in the universe, core collapse supernovae also produce significant amounts of elements heavier than iron through the rapid neutron capture process, known as the R process, in which seed nuclei capture neutrons faster than the nuclei can undergo beta decay, building up very heavy neutron-rich nuclei that subsequently decay to stable isotopes. The R process is responsible for producing about half of the elements heavier than iron, including elements like europium, platinum, gold, and uranium. The site of the R process was debated for decades, with core collapse supernovae and neutron star mergers being the two leading candidates. The detection of gravitational waves from the neutron star merger GW170817 in 2017 and the subsequent observation of the kilonova, a transient powered by the radioactive decay of R process elements, provided strong evidence that neutron star mergers are a significant and possibly the dominant site of R process nucleosynthesis. However, the question is not fully settled, and some fraction of R process elements may still be produced in supernovae, particularly in rare magnetically driven jet events or in neutrino-driven winds from proto-neutron stars. The chemical enrichment of the interstellar medium by supernovae has profound consequences for the subsequent evolution of galaxies and the formation of new generations of stars and planets. The first generation of stars in the universe, called population 3 stars, formed from gas that was almost entirely hydrogen and helium, with only trace amounts of lithium and other light elements produced in Big Bang nucleosynthesis. These stars contained no heavy elements, and their properties, including their masses, luminosities, and lifetimes, were different from those of stars that form in gas enriched by earlier generations of supernovae. When population 3 stars died, those that were massive enough produced supernovae that ejected heavy elements into the surrounding gas. This enriched gas then mixed with pristine gas, and subsequent generations of stars formed from this mixture. Over time, the metallicity of the interstellar medium increased, and the properties of newly forming stars changed accordingly. The presence of heavy elements affects the cooling rate of gas, which determines the minimum mass of fragments that can collapse to form stars. It also affects the opacity of stellar material, which influences the internal structure and evolution of stars. And it provides the raw material for the formation of solid particles, dust grains, and ultimately rocky planets. The existence of Earth, with its iron core, silicate mantle, and biosphere based on carbon, nitrogen, oxygen, and phosphorus, is a direct consequence of nucleosynthesis in multiple generations of stars and supernovae. The energy and momentum injected into the interstellar medium by a supernova also have important dynamical consequences. The expanding shell of ejected material, moving at velocities of thousands to tens of thousands of kilometers per second, sweeps up the surrounding interstellar gas and drives a shockwave that heats the gas to temperatures of millions of degrees. This hot gas emits X-rays and can be observed as a supernova remnant, a roughly spherical shell of hot, expanding gas that can persist for tens of thousands of years. The Crab Nebula, mentioned earlier, is a young supernova remnant with an age of about 1,000 years. The Vela supernova remnant is about 11,000 years old. The Cygnus loop is about 20,000 years old. As a remnant expands, it sweeps up more and more interstellar gas, gradually decelerating, and eventually it merges with the general interstellar medium when its expansion velocity drops below the local sound speed, typically after about 1 million years. The energy deposited by supernovae in the interstellar medium is one of the principal sources of turbulence and heating in the gas of galaxies. It creates a multi-phase medium in which hot, low-density gas coexists with warm and cold, denser phases. The hot gas, heated by supernova shocks, fills a significant fraction of the volume of the galactic disk and can expand out of the disk into the galactic halo, creating a hot, diffuse corona. In galaxies with high star formation rates, The combined effect of many supernovae can drive large-scale outflows, called galactic winds, that eject gas from the galaxy altogether. These outflows play a major role in regulating the growth of galaxies because they remove gas that would otherwise be available for star formation, and they also redistribute metals from the disk of the galaxy into the intergalactic medium. The feedback loop between star formation, supernovae, gas heating and ejection, and subsequent cooling and accretion is one of the central problems in galaxy evolution, and it is incorporated into virtually all modern cosmological simulations of galaxy formation, though the details of how to model it remain uncertain. Supernova remnants are also the primary sites of cosmic ray acceleration. Cosmic rays are high-energy charged particles, mostly protons and atomic nuclei, that pervade the galaxy with energies ranging from about 1 billion electron volts to beyond 10 to the 20 electron volts. The origin of cosmic rays was a mystery for decades after their discovery by Victor Hess in 1912, but it is now widely believed that the bulk of galactic cosmic rays, up to energies of about 10 to the 15 electron volts, the so-called Ni of the cosmic ray energy spectrum, are accelerated at the shock fronts of supernova remnants through a process called diffusive shock acceleration, or first-order Fermi acceleration. In this process, charged particles bounce back and forth across the shock front, gaining energy with each crossing, and a small fraction of particles are accelerated to very high energies before escaping. The observational evidence for this mechanism includes the detection of synchrotron radiation from supernova remnants, which indicates the presence of high-energy electrons, and the detection of gamma rays from some remnants, which can be produced by the interaction of accelerated protons with the ambient gas. The precise details of the acceleration process, including the maximum energy attainable and the fraction of the shock energy that goes into cosmic rays, are still subjects of active research and debate. The morphology and properties of supernova remnants also provide indirect information about the explosion mechanism and the progenitor star. Remnants of core collapse supernovae tend to show evidence of asymmetry, with jets, clumps, and irregularities in the distribution of ejecta. The Cassiopeia A remnant, which is about 340 years old, its light should have reached Earth around 1680, but it was not recorded, possibly because it was heavily absorbed by dust, has been studied extensively in X-rays by the Chandra satellite, revealing a complex structure with knots of silicon, sulfur, argon, calcium, and iron, as well as a compact central object that is likely a neutron star. The spatial distribution of these elements provides a fossil record of the explosion, showing how different layers of the star were ejected in different directions and at different velocities. The asymmetries observed in Cassiopeia A and other young remnants are consistent with the multidimensional simulations discussed earlier, which predict that convection and the SASI produce highly asymmetric explosions. The neutron stars left behind by core collapse supernovae are observed as pulsars, rapidly rotating, highly magnetized neutron stars that emit beams of radiation along their magnetic poles. The radiation sweeps across the sky like a lighthouse beam as the star rotates, producing periodic pulses that can be detected at radio, optical, X-ray, and gamma-ray wavelengths. The first pulsar was discovered by Jocelyn Bell Burnell and Anthony Hewish in 1967, and it was initially so puzzling that the possibility of an artificial origin was briefly considered. The identification of pulsars with rotating neutron stars was made by Thomas Gold in 1968, and it was quickly confirmed by the discovery of a pulsar in the Crab Nebula, the remnant of the 1054 supernova, with a rotation period of about 33 milliseconds. The Crab pulsar is slowing down at a measurable rate, and the rotational energy it is losing is approximately equal to the luminosity of the Crab Nebula, confirming that the nebula is powered by the pulsar's rotational energy, channeled into the surrounding medium through the pulsar wind, a relativistic outflow of electrons and positrons. Pulsars are extraordinary clocks, with periods that are remarkably stable, though they gradually slow down due to the emission of magnetic dipole radiation and the pulsar wind. The most precise pulsar timing measurements can detect period changes of less than 1 part in 10 to the 20, making pulsars some of the most precise clocks in the universe. This precision has been exploited for a variety of scientific purposes, including tests of general relativity. The binary pulsar discovered by Russell Hulse and Joseph Taylor in 1974, consisting of two neutron stars orbiting each other, was observed to be losing orbital energy at a rate that precisely matched the prediction of general relativity for energy loss through gravitational wave emission. This was the first indirect detection of gravitational waves, and it earned Hulse and Taylor the Nobel Prize in 1993. More recently, pulsar timing arrays, which use the coordinated timing of dozens of millisecond pulsars, have been used to search for the low-frequency gravitational wave background produced by merging supermassive black holes throughout the universe, and evidence for this background was reported by several collaborations in 2023. Some neutron stars have extremely strong magnetic fields, more than 1,000 times stronger than those of typical pulsars, and these are called magnetars. Magnetars have magnetic fields of 10 to the 14 to 10 to the 15 Gauss, compared to about 10 to the 12 Gauss for ordinary pulsars. The origin of these extreme fields is not fully understood, but it may be related to the conditions during the formation of the neutron star, particularly the development of a dynamo in the rapidly convecting proto-neutron star in the first few seconds after core bounce. Magnetars are observed as soft gamma repeaters and anomalous X-ray pulsars, and they occasionally produce enormous bursts of gamma rays and X-rays. The most spectacular example was the giant flare from SGR 1806-20 on December 27, 2004, which released about 10 to the 46 ergs in less than a second, making it the most energetic event observed from within our galaxy in the modern era. The gamma rays from this event were so intense that they measurably affected the Earth's ionosphere, despite the source being about 50,000 light-years away. Returning to the question of what determines whether a given star will produce a neutron star or a black hole, the answer is surprisingly uncertain. Naively, one might expect that more massive stars produce more massive remnants, with the most massive stars producing black holes and less massive ones producing neutron stars. However, the relationship between initial stellar mass and remnant type is not monotonic, because the amount of mass that falls back onto the proto-neutron star after the explosion depends on the explosion energy, the binding energy of the stellar envelope, and the detailed density structure of the star at the time of collapse. The density structure, in turn, depends on the star's entire evolutionary history, including its mass loss through stellar winds, which depends on its metallicity and can remove a large fraction of the star's mass before it reaches the end of its life. Any mass transfer in a binary system, and the details of the nuclear burning during the final stages of evolution. Theoretical models predict a complex mapping between initial mass and remnant type, with some mass ranges producing successful explosions and neutron stars, other ranges producing failed explosions and black holes, and still others producing explosions followed by significant fallback that pushes the remnant above the maximum neutron star mass, resulting in a delayed black hole formation. This mapping is sometimes called the explodability landscape, and it has a highly non-monotonic, even chaotic character, meaning that small changes in the initial mass can lead to very different outcomes. The metallicity of the progenitor star, meaning its content of elements heavier than hydrogen and helium, also plays a significant role. Higher metallicity means stronger stellar winds, which strip mass from the star during its lifetime, reducing the mass of the core at the time of collapse. This means that a star with a given initial mass will have a smaller core and a lower mass remnant at low metallicity than at high metallicity, all else being equal. It also affects the compactness of the stellar core at the time of collapse, which is one of the key parameters determining whether an explosion will succeed or fail. The compactness parameter, introduced by Sean O'Connor and Christian Ott, measures the mass enclosed within a certain radius at the time of bounce, and stars with higher compactness tend to be more difficult to explode. The compactness varies non-monotonically with initial mass and metallicity, leading to the complex explodability landscape mentioned above. The role of binary interactions in supernova progenitors is another area of active research. The majority of massive stars are in binary or multiple systems, and interactions between the components, including mass transfer, common envelope evolution, and mergers, can dramatically alter the evolutionary pathways and final fates of the stars involved. A star that loses its hydrogen envelope through mass transfer to a companion will evolve very differently from an isolated star of the same initial mass, and it may produce a type Ib, or IC supernova, instead of a type II. In some cases, the companion star can receive enough mass to become a massive star itself, eventually producing its own supernova, and the system may pass through a phase in which both components are compact objects, neutron stars or black holes, in a close binary. Such systems can inspiral due to gravitational wave emission and eventually merge, producing the kind of events detected by the LIGO and Virgo gravitational wave observatories since 2015. The chain of events from massive binary star formation to double compact object merger can span billions of years and involves multiple supernovae, mass transfer episodes, and dynamical interactions, making it one of the most complex problems in stellar astrophysics. The observational study of supernovae has been transformed in recent decades by the development of wide-field survey telescopes that monitor large areas of the sky repeatedly, discovering supernovae in distant galaxies at rates of hundreds to thousands per year. Projects like the Palomar Transient Factory, its successor, the Zwicky Transient Facility, the All-Sky Automated Survey for Supernovae, and the upcoming Vera C. Rubin Observatory Legacy Survey of Space and Time are designed to detect transient events quickly and trigger follow-up observations with larger telescopes. This has led to the discovery of many unusual and previously unknown types of supernovae, including superluminous supernovae, which are 10 to 100 times brighter than ordinary supernovae and may be powered by the spin-down of a rapidly rotating magnetar, by interaction of the ejector with a dense circumstellar medium, or by pair instability explosions of very massive stars. It has also led to the discovery of rapidly evolving transients, fast blue optical transients, and other events that do not fit neatly into the existing classification scheme, challenging theorists to develop new models and mechanisms. Pair instability supernovae deserve special mention because they involve a completely different physical mechanism, from either core collapse or thermonuclear white dwarf explosions. In very massive stars, with initial masses above about 130 solar masses and relatively low metallicity, which allows them to retain most of their mass, the core temperatures during oxygen and silicon burning can become high enough that energetic photons begin to produce electron-positron pairs. This pair production absorbs energy from the radiation field, reducing the radiation pressure that supports the star, and the star contracts. The contraction raises the temperature further, increasing the pair production rate, and a thermonuclear runaway occurs in which the entire star is disrupted, leaving no remnant. The theoretical prediction of pair instability supernovae dates to the 1960s, but observational confirmation has been difficult because the progenitor stars are extremely rare in the nearby universe, due to the high metallicities of most nearby galaxies, which drive strong mass loss and prevent stars from retaining enough mass to reach the pair instability regime. Some superluminous supernovae have been proposed as pair instability candidates, but the identification remains uncertain. The connection between supernovae and the broader history of the universe extends to the very earliest epochs. The first stars, forming a few 100 million years after the Big Bang from primordial gas in dark matter halos, were likely very massive, with typical masses of tens to hundreds of solar masses, because the lack of heavy elements meant that the gas could not cool as efficiently as metal-enriched gas, leading to higher Jeans masses and larger typical fragment masses. These first stars lived fast and died young, many of them producing supernovae that enriched the surrounding gas with the first heavy elements. The pattern of element abundances produced by these first supernovae is imprinted on the oldest surviving stars in the galaxy, the extremely metal-poor stars found in the halo and bulge of the Milky Way, which have metallicities less than 1,000th of the solar value. By measuring the detailed chemical composition of these ancient stars and comparing the abundance patterns to nucleosynthesis models, it is possible to infer the properties of the supernovae that enriched the gas from which they formed. This field, called stellar archaeology or near-field cosmology, has shown that the enrichment patterns are consistent with core collapse supernovae from progenitors of about 20 to 40 solar masses, with little evidence for pair instability supernovae, suggesting either that very massive first stars were rarer than some models predicted, or that pair instability supernovae are not the dominant enrichment channel. The detection of gravitational waves from compact object mergers has added a new dimension to the study of supernovae and their remnants. The first direct detection of gravitational waves by LIGO on September 14, 2015, was from the merger of two black holes with masses of about 36 and 29 solar masses, producing a final black hole of about 62 solar masses. The detection confirmed a key prediction of general relativity and opened a new window on the universe. Subsequent detections have included mergers of two neutron stars, GW170817, a neutron star and a black hole, and many more black hole binaries. The masses of the black holes detected by LIGO and Virgo have revealed a population that was not anticipated. Many of the black holes are more massive than those found in X-ray binary systems in our galaxy, which typically have masses of about 5 to 15 solar masses. Black holes in the range of 20 to 50 solar masses are common in the gravitational wave catalogue, and some events have involved black holes of 60 to 80 solar masses or more. Understanding how these massive black holes form, and in particular whether they are produced by the direct collapse of massive stars, by hierarchical mergers of smaller black holes, or by some other mechanism, is a major area of current research. The pair instability mechanism is predicted to prevent the formation of black holes in the mass range of about 50 to 120 solar masses. The pair instability mass gap, because stars in the corresponding mass range are completely disrupted by pair instability supernovae. The detection of black holes near or within this mass gap would have implications for our understanding of stellar evolution, supernovae, and the pair instability mechanism itself. And there is some evidence from the LIGO-Virgo catalogue that such objects may exist, though the interpretation is still debated. The study of supernovae has also been intertwined with the development of computational science in a way that is worth noting. Core collapse supernova simulations are among the most computationally demanding problems in physics, because they require the simultaneous solution of the equations of hydrodynamics, neutrino transport, nuclear reactions, and gravity in 3 dimensions, with adequate resolution to capture the relevant instabilities. The neutrino transport problem is particularly challenging, because neutrinos have a range of energies and travel in all directions, requiring the solution of a 6-dimensional transport equation, 3 spatial dimensions and 3 momentum space dimensions, coupled to the hydrodynamics. Various approximations have been developed to make the problem tractable, including flux-limited diffusion, the isotropic diffusion source approximation, and moment-based schemes, but each involves trade-offs between accuracy and computational cost. Full 3-dimensional simulations with detailed neutrino transport have become possible only in the last decade, and even these use approximations and limited resolution compared to what would be needed for fully converged results. The development of supernova simulation codes has been a decades-long effort involving groups in the United States, Germany, Japan, Australia, and elsewhere, and the comparison of results between different codes, using different numerical methods and physical approximations, is an important part of establishing the robustness of the conclusions. One of the persistent puzzles in supernova theory is the neutron star kick problem. Observations of pulsars show that many of them have high velocities, typically several hundred kilometers per second, and some have velocities exceeding 1,000 kilometers per second. These velocities are much higher than the orbital velocities of the progenitor stars, meaning that the neutron stars must have received a kick during the supernova explosion. The origin of these kicks is believed to be related to the asymmetry of the explosion, with the ejector being preferentially expelled in one direction, giving the neutron star a recoil in the opposite direction by conservation of momentum. The multidimensional simulations that include convection and the SASI naturally produce asymmetric explosions, and they can generate kicks of the right magnitude, though the predicted kick distribution depends on the details of the simulation. There is also a possible contribution from asymmetric neutrino emission, which could give the neutron star a kick even in the absence of asymmetric mass ejection, though this mechanism is more speculative and the required asymmetry in the neutrino flux is difficult to produce in current models. The kick velocity distribution has important consequences for the evolution of binary systems containing neutron stars, because a large kick can disrupt the binary, while a smaller kick may leave the system bound, but with an eccentric orbit. The environmental impact of a nearby supernova on the Earth is another topic that has received considerable attention. A supernova within a few tens of parsecs of the Sun could have significant effects on the Earth's atmosphere and biosphere. The intense ultraviolet and X-ray radiation from the supernova could deplete the ozone layer, exposing the surface to increased levels of solar ultraviolet radiation. The cosmic rays accelerated by the supernova remnant could also affect atmospheric chemistry over a longer timescale. There is geological evidence that one or more nearby supernovae may have occurred in the past few million years. Deep-sea sediments and Antarctic snow contain elevated levels of the radioactive isotope iron-60, which is produced in supernovae but not in significant quantities by any terrestrial process. The iron-60 signal peaks at about 2 to 3 million years ago, with a possible earlier peak at about 7 million years ago, suggesting that debris from nearby supernovae was deposited on the Earth at these times. The distance to the supernova that produced the iron-60 has been estimated at about 50 to 100 parsecs, and the possible association with the formation of the local bubble, a region of hot, low-density gas surrounding the Sun, has been discussed. The biological consequences of these events, if any, are uncertain, but some researchers have speculated about a connection to the Pliocene-Pleistocene boundary extinction event. Though this remains highly speculative, the role of supernovae in the broader context of cosmic evolution can be summarized, though perhaps not fully captured, by noting that they serve as the primary mechanism by which the products of stellar nucleosynthesis are distributed into the interstellar medium, providing the raw materials for new stars, planets, and eventually life. They are also a major source of energy input into the interstellar medium, driving turbulence, regulating star formation, and shaping the structure of galaxies. They produce the neutron stars and black holes that are among the most exotic objects in the universe, and whose properties probe fundamental physics at densities, temperatures, and gravitational field strengths that cannot be achieved in any laboratory. And they produce the cosmic rays that fill the galaxy and interact with the Earth's atmosphere, contributing to the background radiation environment and possibly influencing atmospheric and biological processes. The next major observational advance in supernova physics will likely come from the detection of neutrinos and gravitational waves from a core collapse supernova in our own galaxy. The current generation of neutrino detectors, including Super Kamiokande in Japan, IceCube at the South Pole, and the planned Hyper Kamiokande and Dune detectors, would detect thousands to tens of thousands of neutrinos from a galactic supernova, compared to the 25 detected from SN 1987A. This would provide a detailed time-resolved measurement of the neutrino luminosity and energy spectrum during the collapse, bounce, accretion, and cooling phases, testing the theoretical models in unprecedented detail. The gravitational wave signal from a core collapse supernova is expected to be weaker than that from a compact object merger, and current detectors like LIGO and Virgo might only detect it from a supernova within a few kiloparsecs. But next-generation detectors like the Einstein Telescope and Cosmic Explorer would extend the reach significantly. The combined multi-messenger signal of neutrinos, gravitational waves, and electromagnetic radiation from a galactic supernova would be a watershed event in astrophysics, providing information about the explosion mechanism, the equation of state of dense matter, and the properties of neutrinos that cannot be obtained in any other way. The theoretical understanding of core collapse supernovae, while enormously advanced compared to a few decades ago, remains incomplete in several important respects. The question of which stars explode and which form black holes without a bright supernova is not definitively answered. The exact mechanism by which the stalled shock is revived is still debated, with different simulation codes and different physical approximations sometimes giving different results. The role of magnetic fields and rotation, which are expected to be important in at least some fraction of supernovae, is not yet fully incorporated into the three-dimensional models. The nucleosynthetic yields, which determine the chemical enrichment of the galaxy, depend on the details of the explosion in ways that are not fully constrained by current simulations, and the properties of matter at supranuclear densities, which determine the structure of neutron stars and the maximum mass above which a black hole forms, are still poorly known. with the equation of state constrained by a combination of nuclear theory, laboratory experiments, neutron star mass measurements, and, most recently, observations of neutron star tidal deformability from gravitational wave events. Despite these uncertainties, the basic physical picture of what happens when a massive star goes supernova is well established and supported by multiple lines of evidence. A massive star evolves through successive nuclear burning stages, building up a layered structure with an iron core at its center. When the iron core exceeds the Chandrasekhar mass, it collapses in less than a second, reaching nuclear densities and bouncing to form a proto-neutron star and a shock wave. The shock stalls due to energy losses from photodisintegration and neutrino emission, and it is revived by a combination of neutrino heating and hydrodynamic instabilities over a timescale of hundreds of milliseconds. The revived shock propagates outward through the star, ejecting the envelope and producing an expanding fireball of hot gas, whose luminosity is powered first by the shock-deposited thermal energy and then by the radioactive decay of nickel-56. The proto-neutron star cools by emitting neutrinos over about 10 seconds, contracting to a neutron star or, if the mass is too great, collapsing to a black hole. The ejecta expand into the interstellar medium, forming a supernova remnant that can persist for tens of thousands of years, sweeping up ambient gas, heating it, accelerating cosmic rays, and gradually mixing with the interstellar medium, enriching it with heavy elements that will be incorporated into the next generation of stars and planets. This picture, assembled over decades of theoretical, computational, and observational work, is one of the major achievements of modern astrophysics. It connects the physics of atomic nuclei to the structure of galaxies, the properties of neutrinos to the chemical composition of the Earth, and the death of individual stars to the ongoing evolution of the cosmos. It is also a picture that continues to be refined and challenged, as new observations reveal unexpected phenomena, as computational capabilities increase, and as our understanding of the fundamental physics involved deepens. The study of supernovae remains one of the most active and productive areas of research in astronomy and physics, and the next galactic supernova, whenever it occurs, will undoubtedly provide answers to some current questions while raising entirely new ones that we have not yet thought to ask. The complexity of the supernova problem is perhaps best illustrated by considering the range of timescales involved. The nuclear burning stages that precede the explosion unfold over millions of years. The core collapse itself takes less than a second. The revival of the shock occurs over hundreds of milliseconds. The neutrino cooling phase lasts about 10 seconds. The shock breakout from the stellar surface happens hours to days later. The supernova light curve evolves over weeks to months. The supernova remnant expands and evolves over thousands to millions of years. The chemical enrichment of the interstellar medium and its incorporation into new stars and planets occurs over billions of years. Each of these timescales involves different physical processes, and understanding the full chain of events requires integrating knowledge across all of them. The spatial scales are equally diverse. The iron core at the moment of collapse has a radius comparable to the Earth, about 6,000 kilometers. The proto-neutron star has a radius of 10 to 15 kilometers. The standing accretion shock sits at a radius of about 100 to 200 kilometers. The stellar envelope has a radius of hundreds of millions of kilometers for a red supergiant. The supernova remnant expands to a size of tens of parsecs, or about 100 light-years. The chemical products of the supernova are distributed over volumes of kiloparsecs as they mix into the interstellar medium, and the effects of supernova feedback on galaxy evolution are felt on scales of the entire galactic disk and halo, spanning tens of kiloparsecs. The energy scales are also enormous. The gravitational binding energy of a neutron star is about 3 times 10 to the 53 ergs, equivalent to the rest mass energy of about a tenth of a solar mass. The kinetic energy of the explosion is about 10 to the 51 ergs. The peak luminosity of a supernova can reach 10 to the 43 ergs per second, which is comparable to the luminosity of an entire galaxy. The energy carried away by neutrinos, about 3 times 10 to the 53 ergs, is emitted in about 10 seconds, giving a peak neutrino luminosity of about 3 times 10 to the 52 ergs per second, which briefly exceeds the combined luminosity of all the stars in the observable universe. These numbers illustrate why supernovae are among the most energetic events in the universe and why they have such profound effects on their surroundings. The connection between supernovae and the origin of the elements that constitute our world is worth elaborating further. The oxygen we breathe was produced in the cores of massive stars, primarily during helium and carbon burning, and was ejected into the interstellar medium by supernovae. The calcium in our bones, the iron in our blood, the silicon in the rocks beneath our feet, the gold and platinum in jewelry and electronics, all of these elements were forged in stars and dispersed by explosions. The specific isotopic ratios of the elements in the solar system provide detailed constraints on the mix of nucleosynthetic sources that contributed to the material from which the Sun and planets formed. The solar system's composition is consistent with contributions from many generations of core collapse supernovae, type Ia supernovae, asymptotic giant branch stars, which produce S-process elements through slow neutron capture, and possibly neutron star mergers. The identification of pre-solar grains in meteorites, tiny mineral grains that formed in the outflows of dying stars and survived incorporation into the solar nebula, provides even more direct evidence of specific nucleosynthetic environments, with some grains showing isotopic signatures that can only be produced in supernova ejecta. The social and institutional history of supernova research also reveals interesting patterns. The development of the field has been shaped not only by scientific discoveries, but by the availability of funding, computing resources, detector technology, and access to observing time on major telescopes and in space. The construction of neutrino detectors like Kamiokande-TAS and Super Kamiokande was driven in part by the desire to search for proton decay, a prediction of grand unified theories, and the detection of neutrinos from SN 1987A was in some sense a serendipitous byproduct of that program. The development of gravitational wave detectors was a decades-long effort that faced significant skepticism and funding challenges before the first detection in 2015. The Wide-Field Survey telescopes that now discover thousands of supernovae per year were developed for a variety of purposes, including the search for near-Earth asteroids and the measurement of cosmic acceleration. The interdisciplinary character of supernova research, which requires expertise in nuclear physics, general relativity, computational fluid dynamics, neutrino physics, and observational astronomy, has led to the formation of large collaborative groups and the development of shared simulation codes and data analysis tools, a pattern that mirrors similar trends in other areas of physics and astronomy. Looking forward, several developments are expected to advance the field significantly in the coming years and decades. The Vera C. Rubin Observatory, scheduled to begin full operations in 2025, will discover an unprecedented number of supernovae, including rare and unusual events that are currently poorly sampled. The James Webb Space Telescope is already providing new infrared observations of supernova remnants and nearby supernovae, revealing details of the nucleosynthesis and dust formation that are invisible at other wavelengths. Next-generation neutrino detectors will be sensitive enough to detect the diffuse supernova neutrino background, the cumulative flux of neutrinos from all supernovae that have occurred throughout the history of the universe, which has been predicted theoretically but not yet detected. The detection of this background would provide a direct measurement of the cosmic supernova rate and the average neutrino energy spectrum, testing models of stellar evolution and supernova physics. And of course, the next galactic supernova, which could occur at any time, would provide a wealth of multi-messenger data that would transform the field. The persistence of open questions in supernova physics, despite decades of intensive effort, is not a sign of failure, but a reflection of the genuine difficulty of the problem. The physics of core collapse involves regimes of density, temperature, and composition that are unlike anything encountered in terrestrial experience, and the multidimensional, multi-physics character of the problem makes it one of the most challenging in computational science. The fact that the basic mechanism of core collapse supernovae, the delayed neutrino heating mechanism augmented by hydrodynamic instabilities, was not confirmed by three-dimensional simulations until the 2010s, more than 50 years after the mechanism was first proposed, gives some sense of the timescale on which progress occurs. And the fact that significant uncertainties remain in the equation of state, the neutrino interaction rates, the progenitor structures, and the mapping between progenitor mass and remnant type means that there is still much work to be done. The intellectual structure of supernova research, which integrates input from many subfields of physics and astronomy, also means that advances in seemingly unrelated areas can have unexpected consequences for supernova theory. Advances in lattice quantum chromodynamics, which provides theoretical predictions for the properties of dense nuclear matter, can constrain the neutron star equation of state and thus the supernova mechanism. Advances in nuclear experiment, such as measurements of neutron-rich nuclei at radioactive beam facilities, can improve the nuclear reaction rates used in simulations and the understanding of R-process nucleosynthesis. Advances in neutrino physics, such as the determination of the neutrino mass hierarchy and the measurement of coherent elastic neutrino nucleus scattering, can affect predictions for the neutrino signal from a galactic supernova. And advances in gravitational wave astronomy can constrain the population of compact objects produced by supernovae and the physics of matter at supranuclear densities. The story of supernova research is thus not only a story about exploding stars, but also a story about how scientific understanding is built, incrementally and collectively, through the interplay of observation, theory, computation, and experiment, across disciplinary boundaries and over timescales that span human generations. The current state of knowledge represents the accumulated effort of thousands of researchers over more than a century, and the questions that remain open are precisely the kind of deep, interconnected problems that continue to drive scientific progress. The next chapter of this story is being written now, in the observatories, laboratories, and computing centers around the world, and it will be shaped by discoveries that cannot be predicted in advance, as all the most important ones are.